Thank you very much for having me here. So, our new results I'm going to talk about are joined with Bhargav Bhatt, Artem Kanaev, Akhil Mathew, and Mingjia Zhang. Well, all the mistakes are mine. The motivation for this work is the desire to construct so given smooth formal scheme over p-adic integers, what we want to construct a gerbe, GM gerbe over, let me give it a name, so P over the cotangent space to X, that which is an integral interpolation in two kind of objects. So one, well, so X is a scheme over a formal scheme over ZP. In particular, I can reduce it mod P. And I can consider the cotangent space to this mod P fiber. So, and then I have the GM gerbe over mod P fiber, represented by the Azumaya algebra of differential operators. So recall that in characteristic P, this algebra has a very large center, canonically identified with the symmetric algebra of the tangent sheaf, and therefore, well, and moreover, it's an Azumaya algebra over its center. So it gives me a GM gerbe. And another construction is what's called the Simpson gerbe. Simpson gerbe. Gerbe, GM gerbe, introduced recently by Bhatt and Zhang. Which leaves over the analytic generic fiber of my cotangent space. So this is an analytic space over tape ring, tape field CP, so they introduced this gerbe, and it plays a key role in their approach to p-adic Simpson correspondence. I won't talk about this in my talk at all. So, but let me just say that. Well, first of all, actually, their gerbe is defined on a larger space. You can take X, you can take its generic fiber, and you can take the cotangent space to this. And you can think of this as a closed ball of radius 1 inside this. And so there, they have a gerbe defined here, and well, in particular, they constructed a functor from CP local systems on this space to sheaves, coherent sheaves on the cotangent space twisted by this gerbe, Simpson gerbe. That's how it appears. And they prove that this functor is fully faithful if X is. Okay, so
do we have to know anything about Simpson's gerbe except that it's very important?
Yes, but I hope by the end of this talk I will construct for you the integral interpolation. I will not mention this Simpson gerbe at all, but we will have a gerbe over there.
But we will
appear. Okay, so.
And what does it mean, integral interpolation? Do we want, so if you have a GM gerbe on the cotangent bundle, then on the one hand it gives you a GM gerbe over the specials over the reduction mod P. On the other hand, it gives a GM gerbe over the generic fiber, which is an analytic space. And so here we are given on the one hand, GM gerbe, canonical GM gerbe over the cotangent bundle of the reduction mod P, on the other hand, over the generic fiber, and we want to. So we have a problem. It's not a priori not clear that it has a solution, and you claim that it has a canonical solution.
Right.
And does this extension of a gerbe that you will construct to the one that was constructed unique or automatic? You have a gerbe on a disk basically, and you want
you mean this extension along this inclusion?
Yeah.
Whether it's unique or automatic.
It's okay to say that if the answer is not clear, it's okay to say this. Yeah. But anyway, you produce something very canonical.
Right.
So in some sense, it's not terribly necessary to know the answer to such a question.
Okay, so this turns out to be a part of a larger picture. So another, kind of the output of the construction that I'm going to explain today is will be the following. So we will construct a deformation of the category of modules over the link of differential operators on X. Well, X is a formal scheme, so I will consider p-complete modules. Here are p-complete. So of this category, and this deformation, well, first of all, I want to give a name to this. So this is how I will denote it. So this is X, and there is prism subscript with hat. So this is a name for the deformation, and it's deformation that lives over, it's parametrized by a stack. And again, I want to give a name to this. This is ZP prism. Okay, so and so the specialization of this deformation to some particular points of this stack will recover sheaves on the cotangent bundle twisted by this gerbe P that I mentioned, I alluded to. Okay, so
just so presumably this category that you will construct will be really a category of quasi-coherent on
Exactly.
some stack.
I'm going to produce a functor from the category of formal p-adic schemes, p-adic formal schemes to some kind of stacks. Stacks. And so the name for this functor is prismatized. And indeed, as Frobenius suggested, it will be the category of quasi-coherent. Okay. So
and since it's functorial in X, and any p-adic scheme is a scheme over the formal spectrum of Z, it is clear, even without knowing the definition, that X prism hat is a stack over ZP over CP prism hat. And so if you fix a point of CP prism hat, then you can look at a fiber, and then you can take a quasi-coh over this fiber. And probably this is more or less what you mean, that you have a deformation over a stack. So, and then is it true that this prism hat is what you call sheared prismatization?
Right. Yeah. This is
yes.
This is sheared.
And does either one or two? So on this blackboard you have one and two. Does either one or two have to do with some particular point of?
Right. Well, this P, this integral interpolation, has to do with a particular point of ZP prism hat, called the sheared Hodgkin. So, okay, without further delay, let me. So the plan for the rest of the talk, well, it will have three parts. So first, I will recall for you some basic facts about Witt vectors, in particular about ideal W hat in the ring of Witt vectors. And then I will define for you a functor, and then I will try to describe for you some specialization of this. So this is a kind of quite complicated object. It lives over this stack, which is itself quite complicated, but its specialization to various points of ZP prism hat can be understood geometrically. That's what I'm going to do. So okay. So I'll start with the definition. Let R be a commutative ring. So by definition, W hat of R is the following set. It consists of.
By the way, does W denote
p-typical Witt vectors?
P-typical.
Yeah, p-typical Witt vector. So it's consists of all Witt vectors, Vi, Ai. In W of R, with two conditions. Right. So first of all, all AI, such that all AI are nilpotent, and secondly, all but finitely many. Many of them are of AIs are actually zero. Okay, so a good example to think about, so for example, you have, I fix, I should say that I fix once and for all some prime number p. And this W stands for p-typical vectors. So then, I can take the Taylor representative of P. For example, it lives in, Z p to the n, where n some integer, and I claim that this is an example. This is an element here. A non-example is the following. You can take P and view it as an element. And I claim that that's an integer, so it lives in Witt vectors. But I claim that it's not here. In fact, the second coordinate of this integer P is invertible. Okay, so
yeah, I think it's fine.
So here is a claim. So in fact, this for any real car, this subset is an ideal. That's an easy fact, but I want to explain it briefly to introduce some notations that I will need later. Okay, so so we have two elements. Let's try to prove that this is a subgroup. It's closed under addition. So I have the ring scheme of Witt vectors, and it comes with an action of the multiplicative group G. So if I have lambda and I have a Witt vector, Vi AI, then what you do, you just take the Taylor representative of your element in GM and then multiply by this vector. And explicitly, you can write this as sum of Vi. Okay. So this is sum of Vi lambda p to the I times A. Okay. So in particular, this implies that the coordinate ring of W, which is at the end is just a polynomial algebra in infinitely many variables. This is a Hopf algebra, right? Because this is a group. So it has a grade. Is a graded Hopf algebra. Okay. So the gradient is characterized by the property that degree of AI is equal to p to the n. And this follows from, that's this action of GM. It's action by group automorphism, so it follows that this is equated. And in particular, if I have two Witt vectors like this, and I want to multiply them, and I want to add them, so Bj, Bj, then the sum is it's a Witt vector Ck Ai Bj, where all this, where CK is a polynomial, homogeneous polynomial, polynomial of degree p to the k, right? This observation immediately implies that this subset that I defined is closed under addition because, well, first of all, because AI and BI are nilpotent. This guy is also nilpotent. But what is also true is that so eventually, so if these sums are actually finite, then eventually all this CK are going to be zero because the exponents in which non-zero entries will come here will be large, AI and BI. Okay, so right, and I think I will leave it for you to check that it's closed under. So this implies that W is set. And I will leave it for you to check that it's actually. Okay, so now so we also have the Frobenius. Frobenius. It's a map from it's endomorphism of this ring, and the claim is that it preserves this ideal.
Excuse me.
Yeah.
Do you assume that R is well, that P is nilpotent in R?
I don't think so.
You don't. Okay.
At the moment, not. But yeah, wait, I'm going to apply it. So, right. So again, so the Frobenius on Witt vectors is uniquely characterized by the following. So Frobenius, any Witt vector can be written as the Muir representative plus V of something. And the Frobenius is defined by the following formula. So now this formula implies the result. Okay, so another remark. So there are two types of coordinates on the ring of Witt vectors. These are called the Witt coordinates, but there is also Sheared coordinates. There are also Sheared coordinates. So description via Sheared coordinates. So I will recall for you what this is. So this is something, well, it's elementary and very important. So again, if you look at the coordinate ring, then so there is, we have ring automorphism, endomorphism of W, Frobenius, in particular attacks here. And the basic property of the Witt vector Frobenius is that if you plug here a ring of characteristic P, then the Witt vector Frobenius is just given by the fifth power operation on R. And this implies that for any f here, it's Frobenius for any function on this coordinate ring on W. Its Frobenius is equal to f to the pth power plus delta plus p times some other function, which I will denote like this. So it's important that the difference between Frobenius star of f and pth power of f is divisible by. So this makes the coordinate ring into a delta ring, and the effect, which is theory of triviality, is that this algebra is freely generated as a this delta ring is freely generated as a delta ring by single element. Namely, I have function a0, and I can apply to it delta. Right? I can apply to it delta squared, and so on. So let me introduce them. Yeah. So that's an non-trivial result. So I will introduce some notations. So this is y0, this is y1, this is y2. Okay. So and I claim that so claim is that x belongs to w hat of r if and only if all ji coordinates, so yi of x, are nilpotent. And all but finitely many are. Okay, so so you can prove this using the same gradient argument. So the observation is that this is a homogeneous polynomial in usual coordinates in a1, a0, and of degree So this proves that if x is here, then this property of its GL coordinates is satisfied. And well, I will leave it for you to check that very percent. Okay, so so this Witt vector functor is represented by a scheme. It's actually infinite dimensional affine space, but functor w hat is not represented by a scheme, but it's is represented by in denote by them. So if you this fact will not play much role in what I'll follow. Just I want to introduce this notation. You can think of w hat as a okay, so So here is a property of this object. I claim that the Frobenius is surjective FPQC locally surjective. So what does it mean? It means that if I give you an R point here, then you can find the faithfully flat map from R to R prime, and find an R prime point of W hat, such that its Frobenius is a point of W hat you start. So here is it's easier. So it suffices to check this for translation of Eichner representative. So A is nilpotent. Well, first of all, by replacing my ring R by some faithfully flat cover, I may assume that A is a power, so I can write it as Pn of some P to the and then this is equal to V of 1. Now,
so you wrote A as B to the power of P to the N, and you can do this.
Use projection.
Huh?
Then I use.
And here you used FPQC.
Exactly. And now I'm going to use it once again. I'm going to use the fact that the Frobenius on W itself is locally surjective. Yes.
Sorry for interrupting. Am I right? Is it true that if you consider F pre-image of W hat is sub-end scheme in W, and if you consider its pre-image by F, it equals by W hat itself?
The pre-image.
You have Frobenius which acts surjective on W. Is it true that pre-image of W hat by Frobenius is also equals W hat?
No, we'll see. We'll see.
Okay.
We'll see an example. We'll see what happens in a second. So, the question was whether it's true that any element in the Frobenius kernel of on W is in fact in W hat.
In W hat.
Right. It's not true. Right. So now I'm going to use once again. So I will write this element V of 1 as Frobenius of some. The Z is in W of some R. And this is I can write it as Frobenius of so this is also a P power, so I can write it as so I can enlarge in my ring. I can write this B as P power of some B prime, and then it will be B prime times. Okay, so B prime is nilpotent because its large power is just A. And Z is something, but if I multiply an element in W hat by something, it's still an element in W hat. Okay. So this gives surjectivity. Right. Okay, now I'm going to answer Sasha's question. So, and for this, I want to describe the kernel of the Frobenius. Right. So here is a definition. GA sharp. Now, until this point, everything that I said, we worked over integers, and now I'm going to work over integers localized at P. So this is the, so I denote by GA sharp the PD whole of 0 at GA. This is that. So explicitly, this is a affine group scheme, and its coordinate ring is ZP. So you consider the subring. So n here is 1 runs over all integers, and this is subring of Q of x generated by these elements. And the co-multiplication is, it's given by, it's determined by the formula that this is x plus 1 plus 1 times x. Okay. Now, there is a theorem which is I think it's due to Vologodsky, maybe Bhatt and Lurie. It's a very the proof of the theorem is very simple, very short.
It's an observation. Yes.
It's an observation, but since it's it's very important for the theory, I want to quote the theorem. So the observation is that so if you consider the kernel of the Witt vector Frobenius, gain over Z Frobenius, then it's isomorphic to GA sharp Z of P. Namely, there exists a unique isomorphism that makes the following diagram commutative. So GA sharp is defined as a PD whole here. So in particular, I have a map group homomorphism to G. And here I also have group homomorphism, which is given by first coordinate. And so the claim is that there exists a unique map that, isomorphism that makes this diagram. So this is the proof is a few lines, and in fact I will some way write them down in a second. So if you use J coordinates, so I want to, but before I explain something about that proof, so I want to state the I actually want to explain the analog of this result for W hat. So so we have the coordinate ring of GA sharp that I described here, and inside we have ideal, which I will denote by well, it's divided part of the augmentation ideal. So this explicitly is consists of all elements of degree greater or equal than n. So definition. So GA sharp hat is an in-scheme, and it's defined as a colimit of spec of these guys of O GA ZP sharp modular it. So each individual quotient, well, it's not a Hopf algebra, but the limit is a colimit is a group algebra, for instance. So, well, how do you think of this? So, right. So, what is GA? What are R points of this? Yeah. Yeah. Okay. So first of all, it's an R point of GA sharp. So that means that I have first of all I have an element of this thing R, plus I have its divided powers. 2, 3, so on. So these are just collection of elements, divided powers. You I think of gamma n of x as x to the n over n factorial, satisfying the usual relation. So this is an element. This is an element of GA sharp of R with the following property such that gamma n of x is 0 for very large. Right? That's this is by definition. And now proposition is there exists an isomorphism between GA ZP sharp hat and the Frobenius kernel. Yeah, that's my notation for the kernel of Witt vector Frobenius. W. That's notation. And it's uniquely characterized. Well, here the uniqueness is obvious. So this GA sharp hat is a subgroup of GA sharp. Which is clear from this description. And also the same is here. And this this answers Sasha's question. So you see that not every element in the Frobenius kernel on W is here. So this is strictly. I will give a concrete example in a second. Let me say a few words how you prove this. Right. So proof sketch. Suppose let's give ourselves some. I want to construct a map from in this direction. Suppose I have a Witt vector, which is in the Frobenius kernel. So W hat F equals some link R, right? So and then I want to construct this sequence, which is fine. So what you do, you so first you define x. So the sequence starts with x, and you declare that x is just the first Witt coordinate, which is y0. That's the first Witt coordinate of Z. This I am forced to do this if I want this diagram to be commutative. That's what that commutativity tells me. So now I need to explain why this X has divided powers. So now I'm going to use JL coordinates, and I recall that I denote them by yi. And the first JL coordinate is characterized by the following formula. So it's the zero JL coordinate is just the first Witt coordinate. Well, the zeroth Witt coordinate. The first JL coordinate is characterized by this formula. So this is identity in the coordinate ring of W. And now if I apply this identity, if I evaluate these functions at Z, this is zero by definition because Z is in Frobenius kernel. So I'll conclude that P y1 of Z is of Z is y0 So and this is zero. Okay, so that means that you declare that. So because we work with rings where with algebras over ZP, so all we care about are like gamma p to the n of x. So everything else can be obtained from this. So for example, I need to explain why this has p divided power. Well, that's just minus y1 over z over p minus 1. Okay, and you can keep going, and you'll see that this J coordinates gives you all the divided powers. That's the idea. And you see that if because of our characterization of W hat in terms of JL coordinates. So this consists of all Witt vectors whose all JL coordinates are nilpotent and only finitely many of them are not. See that it has this finiteness property. Okay. So here is an application. Questions so far? So suppose let's consider the following Witt vector claim. P minus V of 1. I claim that it's So yeah, maybe, sorry, I want to introduce before this claim, let me introduce one piece of So I wanted to, so let's see. So I want to extend, so notation. So W hat for me is a in-scheme. In particular, I can take its points with values in any other in-scheme. So in particular, I can consider objects like W hat of SPOF R. This is an in-scheme, this is an in-scheme, these are maps. So explicitly, this is just calling of W hat of R. Oh yeah, thank you. Right. So now I can formulate the claim. So I want to consider P minus V of 1. So I claim that this is an element of W hat of SPOF ZP if and only if P is greater than
2. So by the way, without any condition, am I right that this element is killed by F?
Right, and that's what I'm going to use now. So, sorry. So, first observation is what I already said. So f of this, that's the key observation, that P minus V of 1 is that means that have the following. So inclusion. So this is an element of Frobenius kernel of ZP, and which is isomorphic to GA sharp of ZP. So now, what is GA sharp of ZP? First of all, this is a subgroup of ZP that consists of all p-adic integers that has divided powers, and you can convince yourself that this is precisely PZP. And under this equivalence, so remember that I had commutative triangle describing this characterizing this map. So the first coordinate, Witt coordinate of this element is P. So that means that under this isomorphism, the element goes to P, which is now. So inside I have W hat f equals 0 of SPOF ZP, and this is isomorphic to G sharp. Now this is a subgroup here that consists of those elements whose divided powers are topologically tend to 0. So I want to say that P is an GA sharp hat of ZP, if and only if limit of P to the n over n factorial is m goes to infinity is z, p-adic in z. So, and this is known that it's true precisely when p is greater. Okay. So, yeah, one last piece of notation. Need to introduce the group of multiplicative elements in W hat. Well, W hat is not a unitary ring, but well, Volodya explained in his paper that if you have any ring, you can still talk about its multiplicative group.
Well, I don't. I learned this fact as a student at Gelfan's seminar. There were lectures, kind of introduction to K-theory, and in K-theory it is helpful to consider GL n of a non-unitary ring.
Yeah.
So
If you have a unitary ring, then units are solutions to the following equation. But this equation can be rewritten. It's x plus y plus xy equals 0. So if you have any ring, you just look at the group of solutions to this equation. But anyway, this is a curious observation, but definition W hat cross of R is that's a subgroup. So X in W R, maybe I could cross such that X minus 1 is in W. So I consider elements which are very close to 1.
And if so, then so is it a subgroup or just a submonoid?
This is a subgroup.
Subgroup.
Yeah. Am I right that this is a just 1 second? So this is. So do I need to assume that R is p-adic for this or not? Yeah. Okay. So plane W.
So the question is whether the inverse of x, if x minus 1 is in W hat, is it true that x inverse minus 1 is also in W hat? Probably yes, because x inverse minus 1 can be is 1 minus x divided by x. So,
I mean, I think W hat is a null ideal.
what?
I think W hat is a null ideal. So then I think that would imply this.
So I think the answer to my question is false. So what's the problem? The problem is to show, to prove or disprove that if x is a Witt, suppose x is an invertible Witt vector such that x minus 1 is in W hat. Then I think that x inverse minus 1 is also in W hat because x inverse minus 1 can be rewritten as well up to after you multiply x times x inverse minus 1 equals 1 minus x, but 1 minus x is in W hat, and W hat is an ideal. So if you multiply 1 minus x by x inverse, you again get to W hat. So no.
Okay. So Right. So now I am ready to. So that's the first part of my talk. So preliminary. So now I'm ready to tell you what the prismatization.
By the way, it's more or less time for the.
Maybe I will first define what ZP prism hat is, and then it would be a good time for break. So, right. So this is section 2. So, so now for P nilpotent R, I define the set, I will denote it by W prime of R, and I will refer to it as strongly primitive elements. So this is it consists of all Xi in WR, such that Xi is very close to. So so definition, the step, so recall that I want to construct some deformation of the category of T modules, and it's going to be parameterized by a stack. And now I will tell you what this stack is. So this is ZP prism hat. Is well, it's a stack which is F PQC sheafification of the following functor R goes to, it's convenient for me to add one condition. So I will declare that W prime prime of R is empty if R is not nilpotent. Yeah, so that's, and then, okay, so I will define it's a sheafification of the following functor. So I take W prime R. So this is a set, and acted upon by group W hat cross. So, well, so if you clearly this this condition is preserved by multiplication by, well, if you multiply C by any element which is close to 1, this condition is preserved. So so this group acts here, and I consider the quotient, but I consider really the quotient. This is refers to groupoid quotient. So it's not a set. Groupoid quotient. It's not a set. It's a groupoid. Instead of identifying elements, I introduce a category where objects are these and morphisms. So for each pair here, there is a morphism such for each triple x, y here, and an element here such that u times x is y. I have a morphism. Okay, so this is a ring. This is a sheaf of presheaf of groupoids. Then I take its sheafification, and this is my definition of ZP prism.
I want to compare this with ZP.
So that's probably the last remark before the break. Remark. So there is a so Volodya defined the set of primitive elements for p-nilpotent ring R. As follows. So it's a collection of it's a set of fit vectors vi ai in W of R with the following property: ai aa0 is nilpotent, and a1 is invertible. And clearly, W prime prime of R is a subset. So it's a subset. So now ZP prism is defined as a quotient of W prime by W star. So in particular, it receives a map from ZP. So proposition that I might have time, maybe not, it's kind of important. So let's give a name to this map. So pi is a torsor under certain group, and this group is GA sharp modulo GA sharp
Okay, so slightly unexpected is that here the additive group appears.
Doesn't matter. It turns out that you won't change it. This quotient is, I could replace A by M everywhere, and the quotient does not get changed.
And is it evidence that pi is subjective?
It's subjective locally for FPTC topology.
Just on end, the head should be over sharp, or what is the? How do we?
Yeah. So this was introduced. This was the Frobenius kernel on the.
Yes, but should the head be over G or over sharp? Not крышка.
No, I mean, it's.
What are the rules of notation? Because you write W head. And so
yeah, so probably it would be wiser to use this notation.
Okay.
Okay.
And when you consider this quotient, you really, strictly speaking, you mean that for any R, for any test ring R, maybe R is p-nilpotent, you consider GA sharp of R, modulo GA head sharp of R, then you get a pre-sheaf, then you sheafify. So you get some sheaf for the FPQC topology, and at first glance, this sheaf seems to be rather nasty. So it's hard for me to visualize it as a space. Is it secretly nice, or
So this quotient.
This quotient. What kind of object? So
Formally, nothing
prevents us to consider such a sheaf, but is it well?
Yeah.
There are nice objects and
yeah, I don't know. So I don't know. Definitely, I don't think that it's a nice object. So there are two questions: whether this is a nice object from the point of view of algebraic geometry, and whether you can compute points of this quotient. For example, this is G sharp. What you can take a ZP point of this stack and ask how many preimages it has here. So in order to do this, you have to compute something like this. And this, oh sorry, there is a, and this is it's not easy. I mean,
when you write
ZP points, does it mean
so this means that you first compute
Z mod P to the n points and then pass to the to the
yeah. So
is it something that describes the difference between something like nilpotent crystalline divided powers and usual divided powers?
So there is a map from here to like this, right? Yeah, and I should write everywhere spell, but it's yeah. And this is easy to compute, and as Sasha suggested, it's just well, for example, this is PZP, and this is also a PZP if P is greater than 2, and it's slightly smaller than P is. It's 4Z. It's P squared ZP when P is 2. So that means that this quotient is either consists of one element, single element when P is greater than 2, or it consists of two elements when P is 2. But so this map a priori is not surjective, because a point of this quotient is a torsor under this group, together with a trivialization of the associated GA sharp torsor. And torsors under this group, well, that's not easy to describe. This is co-kernel of the Frobenius on well, it can be described, but it's not. It requires
just one. So you explained that something
is not easy to do, but have you? Do you know the answer to this?
Yeah, I know that this is point when P is greater than 2, but I don't know. I don't know. I know that it has at least 2 points when P is 2. In fact, even this set, I explained that it has 2 points when P is 2. So.
But you don't know whether it has.
Yeah, I don't know about the torsors.
Many points,
yeah,
for instance.
Yeah. But this proof is, well, it's not that easy. It's uses some.
But I asked a stupid question. Is it something that describes you the difference between nilpotent divided power completions and usual divided power completions?
No, I thought that it is this quotient that describes
this. It is this quotient. Okay, yes.
And the difference between this is measured by something that I don't know. I mean, how to visualize. Does it make sense?
Yes, but just. What I said is probably just tautology.
So it's a good time for a break.
Yes.
Recording in progress.
So I defined for you the prismatization, shared prismatization of points. So this is a stack, and so it has an S structure. It has action of the Frobenius. So Frobenius, well, sorry, I will call it phi, and Frobenius of this is just the Witt vector. So whenever I have a strongly primitive element, Frobenius applied to C is also a strongly primitive element just because P is fixed under the Frobenius. Okay, so and now I want to describe for you the shared prismatization factor. Well, I want to first make it slightly, the goal slightly more precise, shared prismatization. Prismatization. So that's supposed to be a functor from formal schemes to stacks, but now stacks over this. And as a functor to this target category, I want this to, well, first of all, I want this stacks, I want this kind of, I want this, well, the prismatization of any x carry an action of the Frobenius. Well, I should not say it like this, but I want to have Frobenius on prismatization of any x. And in addition, I want this functor to commute with commutes with products. Okay, so let's forget about the Frobenius for a second. So if you have a functor that commutes with products, in particular, it carries any group object here to group object here, any ring object here to a ring object here, and in particular, this can be applied to GA. So, and this is the the main part of my talk will be the description of GA hat as a ring stack over ZP. Right? So it turns out that the rest is so once you have this ring stack, there is at least a natural candidate for this functor. You just have to add a few magic points.
So there is a letter capital F here. Off. It's just not capital off.
Sorry.
Yes. Okay.
Okay. So that's the really the main the key construction.
Yes. And once we have such a ring stack, there is a channel machine. But I forgot the name. Transmutation, which produces a functor.
Yeah. Okay, so how? Let's define this.
And this would be a ring stack over the shared prismatization.
Right, over the shared prismatization. So, well, first I want to recall for you how you define the usual prismatization. So suppose we have a primitive, some ring, nilpotent ring R, and a primitive Witt vector. So the definition that was suggested by Volodya for prismatization of GA.
And also by Lurie, of course.
Yes. Yeah, and also had Lurie dependently. So it's the following. It's again. So what I'm describing for you. So I fix a point on this space, and I'm describing for you the fiber of this ring stack over this point, which is supposed to be a ring stack over R. So in particular, it's a functor on R prime algebras, on R algebras, functor that takes values in in ring objects and groupoids, something like this, in rings, let's say. So, and here is the formula for this functor. You take code of W of R prime, W of R prime. The map is multiplication by X. Okay. So, so what is written here? So first of all, as a step, just a quotient of W by the action of W. Well, it's a translation action precomposed with multiplication by disks. It's also clear that this is in fact a group object in groupoids. Well, it's a group stack, just because this is it's a length 1 complex. So there is an equivalence between the category of length 1 complexes and the category of strictly commutative Picard. So this is but in fact this has a ring structure, and this is like an ideal. It has an action. So Volodya has a name for this. It's a quasi-ideal. Quasi-ideal is the same as a strictly commutative differential gradient algebra, concentrated at homological degrees 0 and 1. Homological. So it's believable that this is a kind of it's a ring. It's a kind of quotient of a ring binary. So that's definition of.
Sorry, this formula defines you as already a sheaf of groupoids, right?
Yeah, so you don't need to sheafify.
Okay.
You don't. But you need to say some words why this is really a ring stack. So what you essentially need to explain is that you have to suppose you take this C and you multiply it by some invertible bit vector U. You have to explain why this con does not get changed, which is now I need to tell you how to modify this. So now suppose that my Xc has a stronger condition that is strongly primitive. So I want to construct some ring stack GA is head Xc. So there will be a ring map to GA without that. And the fiber of this map will be a familiar object. It will be GA sharp modulo GA sharp. Right? So this is a fiber sequence of this is the fiber of this map. Okay? So here's what we do, how we do this. First, let me rewrite. So this is one possible kind of module for. So let me rewrite this instruction. So the idea is, first of all, rotate this by 90 degrees. And secondly, take the pullback with respect to the Frobenius. So, So, and I will call this pullback I prime. Right? So the Frobenius on Witt vectors is, so this is a Cartesian diagram. So the Frobenius on Witt vectors is surjective. So in particular, it means that this map, and also I need to, because it depends on C, I want to put it here. So this map induce an isomorphism between the ring stacks W goes to. Right? So this is just another presentation for the same ring stack. And now I'm going to define for you a sub-ideal here. We'll call it I. So what is I prime? So, well, by definition, so it's a fiber product. So it consists of pairs x, comma y, w hat, in w square, w times w, with the following property. So I think of x sitting here and y sitting here. And the property is that f of x equal to c xy. Now, the main idea is to rewrite this equation. F of x minus v of y is equal to c minus p times y. So now what you see here, you so you have y, and you have another quantity whose Frobenius is very small because c is strongly primitive. Yeah. So you can make this even. Now, so you will define I. Definition. This is set of pairs here, such that this quantity x minus vy is in W hat. So, so the Frobenius of this expression is in W hat. Yeah, so this is in W hat, but it doesn't imply that the preimage of W hat inside W is larger than W hat. So this is non-negative. So what we have here is a so we defined sub-ideal, and it maps surjectively to W. So the kernel of this map is GA sharp. Well, because this is a quasi-isomorphism, this must be also GA sharp because of surjectivity of F. So, and the kernel of this is GA sharp F. Right? So in this diagram, all the rows are short exact sequences. So now GA sharp GA prism sheared prismatization point C is defined to be the point. Okay, so it's almost correct. So this is definition. it's only almost correct.
Just so it's not final.
It's not a final. It's a correct definition if p is greater than 2. And if p is equal to, it has to be modified. So I want to explain why. So I will modify it slightly, but first I want to motivate this. It's kind of, it looks a little bit strange now. Okay, maybe I can first give a formal definition, then I will modify. So consider the following element U in this is defined as so you consider P minus diagonal representative of, it's a Witt vector whose first coordinate is 0, so you can apply the inverse. And moreover, this element is a unit because the second coordinate of P is invertible. So it's a unit. And the claim is that U plus minus 1 of W prime. So if I take a primitive, a strongly primitive Witt vector, and I multiply it by this unit, I again get a strongly primitive. So of course I get a primitive element, right? Because if you multiply a primitive element by any unit, you get a primitive element. But a priori not strongly primitive. This claim is trivial if P is greater than 2. In fact, if maybe this is the second part. So if P is greater than 2, then U, okay, P greater than 2, so it should so if greater than 2, then U is in W prime. So, but it's not true if P is 2. So, therefore, well, assuming this claim, which is really kind of a straightforward computation, multiplication by U acts on the quotient. Which is ZB. And this action is trivial when provided that P is greater than 2. Because in this case, by B, this is element of W. So the only modification is that I want to multiply this by U inverse. So you can think of this way. So previously I defined for you some ring stack that lives over here. And now this space has an automorphism, which is in fact an involution. But this may be not that important. So, and I just want to pull it back with respect to this automorphism, right? So, okay, now that's the definition.
So again, you said that U acts on this guy, and the action is trivial
if P is greater than 2.
And who is in evolution?
The claim is that, okay, so claim C is that U squared is in W cross C. Another curious fact is that Frobenius of who is also here. Okay, so that's this is now I want to explain. I want to explain the. Oh, maybe I don't have. I need to write a diagram, so I will write it here. So. So a basic structure.
So did you define?
Yes.
So what? So if P equals 2, then what is the definition?
So I just added U inverse.
Mm-hmm. Yes, so of course you can do it, but it's not clear why you have to.
Yes, so let me explain this. A basic structure that we have on the usual prismatization is the Frobenius. So let's first recall how the Frobenius. So we have a GA prism C, and the Frobenius phi is a map from this from the fiber over point C to the fiber over this point. And in this presentation of the string stack, so it's given just by a map of quasi-ideals. So this is the Frobenius, Witt vector Frobenius, and this is something that I will write down formula. And this map here is my phi. Right? So and the formula for this upper arrow is very simple. You just take x comma y and send it to f of x. So the Frobenius is given by just by Witt vector Frobenius. So and clearly this equation is preserved. But now suppose remember that this has a define some subideals. This is f of c. And ideally, we would like to have this map to preserve the quasi-ideals. So what we want is that what we want to have if x minus v of y is in w hat, then f of x minus v of f of y is also in w hat. Right? So because this is by definition of I. So now this is let's just write what this is. So f of x minus v of f of y. Well, the problem is that f and v do not commute. So this is equal to f of x minus v of y plus some correction. And the correction is p times v of minus 1 times 1. So now the first term here is in W hat, but the last term, well, so if P is greater than 2, so then this is in W hat, is in W hat for P greater than 2. So, and as I said, that when P is greater than 2, you don't need any corrections. So that just works. When P is 2, you don't have the Frobenius, right? That's why I want to modify it. So I claim that, now my basic claim is that there is a map, so Frobenius, so it works for all P now. So this is a map from I U inverse from this quasi-ideal to this quasi-ideal. And I will just write down the formula for you. So x comma y goes to f of x u over f of u times f of y. There is something to check here, but it's not that difficult and it works. So this gives you Frobenius for P equal to. It's a bizarre construction. Bhargav explained to us yesterday kind of a more conceptual approach, but it's well, first it would require like longer. It would require some cleaning. So that's the definition. And I would like to finish by there's a fun part by explaining some example specializations of this, right? So some of those specializations are not unexpected. Right. So so examples. Right. So first of all, so what I mean by examples, so I will look at some points of ZP using hat. I'll try to describe for you the ring stack and prismatization, sheared prismatization, for the fiber of sheared prismatization over this. So the simplest example, well, the first example is what I will call the Rham point.
So just a moment. So in the case of the usual prismatization, there are I think two interesting points: the Rham point and the Hodge state.
And here we will have the Rham point, and for p equal 2, we will have also the crystalline point. And it's not equal to the Rham. And this corresponds to the fact that the fiber over the Rham point of the map from sheared prismatization of ZP to usual prismatization consists at least of 2 points. So, right. So this point corresponds to Xi equal the Rham point. Corresponds to Xi equal to in my notation it's U times P. Again, if you're not in characteristic 2, then you can erase it. It doesn't change the point. If in characteristic 2 you need this, so and so then the fiber which is denoted by GA de Rham hat. And this is GA facing over this point, U times P. Yeah. Is this definition. So this is by that formula over there. This is cone of the map from IP to W. And IP consists of all Witt vectors, pairs of Witt vectors in W, such that, first of all, P, such that Frobenius of X is equal to P times Y. And secondly, X minus V of Y is in W. So, okay. So if you let's rewrite this equation. This equation is equivalent to saying that Frobenius of X minus Vy and minus Vy is 0. So what we have is Y plus an element in W hat which is in the Frobenius. So that means that this is isomorphic to W plus GA sharp. So the second coordinate is Y, and the first coordinate is this expression. And the map from here to W is since it sends so I will call this Z. So then it sends Z comma Y to Z plus V of Y. So that's this cone is G computed explicitly. So and this is very now. So you can observe that this cone. So let's project this W to the first to GA using the first Witt coordinate, and this project to GA sharp. So this is really the cone. Right. So. Right, so that's really the first example of the sheared prismatization. This is the sheared prismatization, the kind of the de Rham point of the sheared prismatization of A1 computed at de Rham point, and at least the motivation for the terminology is the following: the category of quasi-coherent sheaves on the stack is equivalent to the category of p-complete zeros. With no.
Yeah. So this would be the most naive if somebody sees the notation dr sharp. So the GA de Rham is after all the cone can be described as the cone of the map from GA sharp to GA, and so it's natural to expect that dr sharp corresponds to replacing GA sharp
Yeah.
So this is the most natural, the most naive thing.
Yeah. So as far as I understand this, well, Volodya explained in his lecture in Princeton. The kind of the most naive definition of the classical de Rham staircase would be this. But from this perspective, it's not at all clear how you actually deform it. And so kind of the main step in this kind of discovery of prismatization was the observation that this ring stack is isomorphic to this one. It has a Witt vector model. Once you observe this, you have something to deform. You can deform this number p. And so I mean, I didn't really kind of explain how we arrived at this shared prismatization, but the idea was to construct the deformation of this ring stack. And the question is, what is Witt vector model for that? Okay, so this is example 1. Example 2. So crystalline point. So it's raw Chris. So it's a map from also from here to him, and it's given by point C equal P. So notice that this point is stable under the Frobenius. That point, in fact, it's not stable. Well, it is stable if P is greater than 2. But if P is not equal to, is equal to that point, U times P is not stable under the Frobenius. There is no Frobenius on this sheared Rham stack. But this will have, and so it's ZP using now so what to say about so all I want to say is that okay, so by definition, this is a so this is GA at point P, and so it's defined as a cone of some quasi-ideal U inverse times P of R goes to W of R. So so the main observation that I want to make here is that this ring stack is an FP algebra stack. So what does it mean that it's an FP algebra stack? It means that there exists there is a map from FP to this animated algebra. So it means that there exists a map of quasi-ideals like this, where this is multiplication by. So it means that there exists an element here that goes to P here. And so if you write down a formula for this, it consists of, by definition, it consists of all x, y in w times w, such that f of x equal to u inverse p y, and something is small, x minus vy is in w. So, and I need to solve this equation. So so this map takes x, y to x. So I need to show that I can find y. So I need to show that point P has a preimage. And so if I take x, y equal to P times, U, then its image is going to be x. Right, so this is a point here, and under this map it goes to P. So that means that this is an FP algebra stack. So
you claim that PU belongs to I, to this I.
Right. Yes. There is a stronger statement that I want to make. So once we have prismatization of defined this ring stack GA hat, we can talk about prismatization of any scheme. And the claim is that FP prism hat is for usual prismatization. This is still of Z. And the point, right? So this is ZP. So this is raw case.
Just so.
So in particular, so we have x. Well, we have functor from. So it's because it's an FP algebra stack. This sheared crystallization of x depends functorially on x. So when p is greater than 2, this was discovered by Grothendieck that in fact this is just the Rham stack, the sheared Rham stack of x, and it was discovered by Grothendieck that the category of D modules on a lift of any FP scheme depends only on does not depend on the lift. And when P is 2, this so it turns out that there is a kind of description of this in classical terms using Barth law rings of differential operators, but time is too late, so I will not. Maybe I will give just the last example.
Just one. So you are skipping something, and you have to do it. But at least, what is the name of what?
Higher order differential operators, and
but all this is necessary to describe.
Well, this. So I'm saying that.
In other words, if I ask you privately about this, how should I formulate the question? Please tell me about what?
Description of this stack and characteristic for p equal to. Okay, So the last example will be the hot state locus. So example 3. So I have point C, which is VU. I recall that this is P minus square bracket of P. And this is definitely a stronger primitive element. All P. And therefore it defines a map from spf ZP to to ZP prism, shared prismatization. So it's given by this strongly primitive C. But well, I recall that this is a quotient of W prime by a certain group, and so this group does not act here freely. So some points have automorphisms. For example, this point. So what are automorphisms of this point? So automorphism of this C. Well, by definition, it consists of all x in W cross, such that x times this C is C. And one-line computation shows that this group of automorphism is G M sharp hat. So that means that this factors through BGM sharp hat. And this is called the sheared hot state. Concrete, well, it's equivalently, it can be described as, well, inside this W prime, you have primitive Witt vectors whose first coordinate is 0. And that's precisely the image of this map. So,
just what, so this map rho hot state, is it an embedding?
It's a closet embedding. And it fits inter fiber sequence. So you have ZP prism head. You have the Artem Kanaev map to one more GM given by the first Witt coordinate, and inside you have BGM. This is a closet embedding. And the fiber is ZP hot state, which is identified with BGM sharp. So that's differential. So now one last remark. So you can compute hot state well, prismatization of any scheme. In particular, you can apply it to the ring of integers in the tail field C. And you can compute its hot state shared prismatization. it happens to be SPEF OC. Well, this Hodge-Tate prismatization always maps of any scheme maps back to the original scheme. So the canonical map here happens to be nice. And so if you finally if you have any smooth scheme over OC, for example, for a smooth x over SPEF OC, this Hodge-Tate sheared, well, this x Hodge-Tate hat is that meets a map to x, and an easy claim is that this is a VTX sharp hat torsor. So this CX hat sharp is Cartier dual to the cotangent bundle. So a torsor under this gives a GM gerbe P over C status. That's the gerbe that appeared in the introduction. I think I still have to stop here.
Are there any questions or comments?
Can you describe the whole prismatization for SPEF OC?
So I was hoping that this is given by Ainf, but is it true?
I think we did. So I think we.
But when preparing to this talk, I understood that I can't prove this.
Okay, I think maybe we didn't completely test, but I think our belief was that it would give you exactly the same as the usual prismatization for a perfectoid, right?
What is strongly primitive? How you? So that means that you need to in particular, you have a strongly primitive element in bit vectors of Ainf. What is it?
So I think another thing we said is that anytime you have a primitive element and you apply Frobenius to it, it has a strongly primitive representative. So in this case, then you can apply Frobenius. At least that tells you that there is a strongly primitive.
So that's a very good remark by Akhil that the Frobenius on prismatization factors through sheared prismatization. If you imagine it, yeah.
So can you write something on the blackboard?
Yes. So you have the canonical map from X to X sheared prismatization. So that's we have by construction. On the other hand, we have a map from X prism to itself given by the Frobenius. And the claim is that there exists error like this that makes the diagram commutative. It's kind of natural to expect. Imagine that we work with Rham stacks. Then if you take a D module and you take its Frobenius pullback, you get something with this locally nilpotent p-curvature versus nilpotent p-curvature, which actually is zero p-curvature.
And other questions or comments?